Hi guys! Our group was assigned to discuss about a certain study that focuses on the bioremediation of co-contaminated soil with heavy metals and pesticides. As we all know that soil plays a very important role in life support system. Without soil, human life, animal life, and life of microorganisms would be very difficult. In soil, there are also soil microbes which they are dynamic component of soil and perform different beneficial functions in soil system. So let's go to the details of this study. So first, soil contamination is a serious problem due to the large scale and long-term application of hazardous waste caused by the development of industry and agriculture. Both inorganic and organic contaminants including heavy metals, pesticides, petroleum hydrocarbon, and polycyclic aromatic hydrocarbons can affect the quality of function of soils. And there are also many strategies are emerged to control the problems of co-contaminated soil of the heavy metals and pesticides. So guys, let's all listen to my other groupmates which they will discuss about the influence factors, mechanisms, and evaluation methods. So let's begin.
The ideal outcome of bioremediation is that the polluted sites can be restored to their original conditions without any harmful effect to the environment. Living organisms such as microorganisms and plants have shown the ability to remediation of co-contaminated soils with heavy metals and pesticides. According to the type of living organism involved in the process, bioremediation can be divided into microbial remediation, phytoremediation, and combined remediation. Microbial remediation is a safe and eco-friendly technique for soil contamination. Microorganisms have vast catabolic potential for bioremediation of pollutants and then break them down into less active or less toxic compounds or immobile them. Actinobacteria are used as an effective option for the remediation of co-contaminated soil with hexavalent chromium and pesticides. A research found that the bioaccessibility of lindane decreased by 42% and of hexavalent chromium decreased by 52%, demonstrating good results for lindane and hexavalent chromium remediation after supplement with Streptomyces species M7, isolated from co-contaminated environment with heavy metals and pesticides. Meanwhile, an Actinobacteria consortium are also a promising biotechnological tool for degrade lindane and reduce hexavalent chromium from co-contaminated soils, especially in real co-contaminated soils. An Actinobacteria consortium formed by Streptomyces species M7, MC1, and A5, and Amycolatosis tucumanensis AB0 were inoculated in 6 different real soils co-contaminated with lindane and hexavalent chromium from Lerma Valley at the province of Argentina. After 14 days, 5 of the 6 were successfully remediated. The biotransformation and biodegradation process in microbial metabolism of actinobacteria accounted for the reduction of hexavalent chromium to non-toxic chromium ions and the removal of lindane, respectively. Except for hexavalent chromium, microbial remediation using bacteria or fungi is used to remedy soil co-contaminated with pesticides and several common heavy metals including cadmium, copper, lead, zinc, and arsenic. Different to actinobacteria, the bacteria selected to remediate co-contaminated systems by heavy metals and pesticides are mainly engineered bacteria. The pesticide-degrading bacteria have been endowed artificially with heavy metal removal capabilities to remediate mixed pesticide heavy metal contaminated sites. A research succeeded in using engineered gamma-hexachlorocyclohexane, commonly known as lindane, degrading Sphingobium japonicum UT26 to simultaneously detoxify cadmium, chlorpyrifos, and lindane in a liquid environment in the laboratory. Similarly, another research found that bioaugmentation can be effective in promoting organic degrading in co-contaminated soils. Besides, some studies focused on the possibility of the pesticides degrading bacteria that showed resistance to heavy metals to degrade pesticides in co-contaminated soil by heavy metals and pesticides. For example, a research found that cypermethrin has been degraded by Bacillus species AKD1 when multiple metals were present. The Cupriavidus species YNS85 degraded more than 55% of the initial pentachloronitrobenzene with the presence of arsenic, copper, and cadmium in aqueous solution. Fungi have also been studied and applied in remediation of co-contaminated soils with heavy metals and pesticides simultaneously, and most of them are mushrooms. Compared to actinobacteria and bacteria, mushrooms can uptake contaminants from soils into their body and are easier to separate from the soil. The presence of mushrooms leads to a higher microorganisms counts in soil, which consequently resulted in microbial degradation of pesticides. Clitocybe maxima, Pleuretus eryngi, and Coprinus comatus successfully remediated co-contaminated soil with heavy metals and pesticides through microbial degradation. Spent mushroom substrate also has the remediation potential for heavy metals and pesticides co-contamination. A research applied spent Lentinus edodes substrate to a cadmium dichlorophene co-contaminated soil. The degradation rates of DCP ranged from 85% to 96.9%. The bioaccumulation of heavy metals and biodegradation of pesticides had also been discovered in other genera of fungi. Remediation of pollutants from the environment by green living plants is defined as phytoremediation. Some plants show incredible tolerance and remediation capabilities towards heavy metals and pesticides co-contamination. Plants extract pollutants by root systems, translocate them from roots to shoots, and then accumulate or transform heavy metals in the body or degrade or mineralize pesticides in the metabolic processes. Meanwhile, root exudates facilitate the establishment of rhizospheric microorganisms and the increase in bacterial community diversity, both of which promote pesticides degradation. Initial attempts for phytoremediation of dichlorodiphenyl trichloroethane or DDT and cadmium co-contaminated soil were performed by researchers in a province in China using Riccinus communis. They investigated the ability of 23 genotypes of Riccinus communis to remediate cadmium and DDTs simultaneously in the co-contaminated soil. Several other plants had been shown their ability to remediate heavy metals and pesticides co-contaminated soils, including Medicago sativa L, Lolium perennea L, Cucurbita pepo, and Spinacia oleracea. However, sometimes the remediation potential of plants is not as good as expected. A research evaluated the phytoremediation potential of Phragmites australis in co-contaminated soils with phencyclidine or PCP and cadmium. The BF and TF values of cadmium were inferior to 1.0, and the dissipation of PCP was significantly influenced by the presence of cadmium. Thus, Phragmites australis cannot be useful for phytoremediation. Similarly, high concentration of PCP inhibited the degradation of PCP and the accumulation of cadmium in Z-mace L. Another research found out that the Lupinus luteus L growth was suppressed and endophytes were hard to colonize in plants with real landfill soils co-contaminated with heavy metals and organic compounds, even in the lowest degree of pollution. The failure of this phytoremediation is mainly due to the joint stress of heavy metals and organic pollutants. The joint stress of two contaminants may cause the following phenomena. First, the plant growth is significantly influenced by heavy metals, organic pollutants, and their interaction. The total plant biomass is significantly decreased. Second, the uptake and translocate of pollutants by plant is limited. Third, the change of rhizosphere microbial population and activity and or root physiology were unbeneficial to the organic pollutants dissipation and metals uptake. Fourth, soil biota were synergistically inhibited. And fifth, endophytic bacteria colonization failed.
Good day, I am Glaiza Amor and I will discuss what a combined remediation is, the abiotic factors and the physical and chemical properties of soil. First, what is a combined remediation? Combined remediation technology refers to the combination of two or more remediation methods to realize the remediation of pollutants and improve the remediation efficiency. Plant microbe remediation is the most widely used combined bioremediation technology in the field of co-contaminated soil bioremediation. Plant microbe remediation can take advantage for both plant and microbe. First, microorganisms improve the bioavailability of heavy metals and pesticides in soil, which is beneficial to the uptake and accumulation of heavy metals and pesticides by plants. Second, plant root systems provide the best place for microorganisms' growth. Next, we will discuss about abiotic factors. Abiotic factors can significantly affect the bioremediation of metals and pesticides, such as the pH, the temperature, soil moisture, soil type, redox potential, and the cation exchange capacity. Physical and chemical properties of soil. First, soil pH can affect bioremediation in many ways. Metal bioavailability. The soil pH value decrease, generally causing the increasing of metals bioavailability in soil solution. The first reason is, at lower pH, the exchangeable capacity between metal cations and the surface of soil particles is larger than at higher pH. The metal ions from clay mineral particles and the surface of colloids will come into the soil solutions. The second reason is that the dissolution precipitation equilibrium among metal ions will be broken at a lower pH. Hence, the metal ions will be released to the soil solutions. Second, microbes. Different species have different optimal pH range, causing microbes can be affected by pH. And the redox and solubility of metals are also affected by pH. Different forms and valence states of metals make different toxic effects on microbes. Third, the adsorption processes. Changes in pH also affect the effectiveness of binding metal ions in absorption reactions. Fourth, the organic component in soil. With increasing pH, the affinity of ligand ions to metal cations is released for the dissociation of the functional groups of organic components in soil, such as alcoholic, carbonyl, carboxyl, and phenolic functional groups. And fifth, the process of metal uptake by plants. Generally, metal cations will be activated at a lower pH, while metal anions will be more soluble at a higher pH. However, at extreme pH, the microbial degradation processes are inhibited. Some still have potential to remedy pollution in suboptimal conditions. The second property is the soil temperature, wherein it is a crucial factor influencing the bioremediation of metals and pesticides. First, with increasing temperature, the solubility of metals and pesticides are increased, and thus the bioavailability of metals and pesticides are also increased. Second, Temperature also influences the physical nature and chemical composition of organic pollutions. The absorption and desorption process of metals and pesticides on microbes or soil particles can be directly influenced by temperature. In an appropriate context, the adsorption capacity and adsorption intensity will be increased with increasing temperature. And third, temperature influence microbial growth, activity, and degradation potential. In a suitable range, the increase of temperature is beneficial to the degradation of microorganisms. The third property is the soil moisture. Inappropriate soil moisture can hinder the bioremediation process. Low soil moisture content limits the growth and metabolism of microorganisms, while high values reduce soil aeration. Normally, at higher soil moisture levels, more clearly metal uptake can be observed. Next, the soil type. It is a critical factor for the bioavailability of metals in soil. The availability of metal ions and pesticides is closely related to the texture of soil particles. The lowest availability is in fine texture clay soils followed by clay loam, and the highest availability is in loam and sand. The differences in soil type may also affect the interaction between metals and pesticides. The last property is the soil cation exchange capacity or the CEC. It is a measure of the capacity of soil constituents to keep metal ions. With the CEC increasing, the availability of metal ions is decreased. Thus, the lower the CEC, the less metal ions are immobilized and the availability of metal ions in soil is higher. Migration, transformation, and bioavailability of metals can be affected by surface adsorption, ion exchange, and coordinate complexion between metals and some soil compositions, like humic acids and low molecular weight organic acids.
The effects of pollutants and bioremediation processes can be subdivided into two aspects. First is the presence of metals and pesticides themselves, which affects the organisms directly. Second is the presence of coexisting pollutants. The co-occurrence of heavy metals and pesticide can exert either positive or negative effects on biological growth, depending on species, growth stages, concentrations, and properties of contaminants and soil conditions. Heavy metals affect biological activity through a number of metabolic pathways. Once be taken up by the cell, metal cations can interact with various organic ligands such as cell membranes, enzymes, nucleic acids, and proteins of organisms. In some cases, the binding is beneficial. Low metal concentrations can stimulate biological activity such as calcium, copper, manganese, magnesium, and zinc. However, generally, metals can inhibit enzyme or protein activity by disguising themselves as catalytic active groups or by changing protein structures. Toxic metals can hinder any all biological activity, causing different types of responses. Despite the potential toxicity, many organisms can grow in metal-contaminated areas because of resistance or tolerance mechanisms. However, its biomass, physiological morphology, growth, microbial activity, and mycelial colonization will still be affected to varying degrees. The interactions between heavy metals and pesticides can affect the bioremediation processes. The bioavailability of pollutants can be affected by coexisting pollutants. Firstly, the adsorption or desorption kinetics of pollutants in soils is mutually affected by their competition, while the bioavailability of the adsorbed pollutants depends on the adsorption capacity and desorption rate. Secondly, metals complexate with the co-occurrence organic pollutants to form metal-organic complexes. Especially metal cations have a high affinity with electron-rich organic pollutants in forming cation pi bonding, leading to which is described as salting-in effect. The formation of metal-organic complexes changes the existing forms of pollutants, Thus, the solubility, bioavailability, and toxicity of pollutants are affected. Thirdly, besides complexation reaction, other chemical reactions can occur between heavy metals and pesticides. For example, catalytic redox reaction may occur when organic pollutants coexist with metals with high oxidative potential. The main models of metal effects on organic pollutant biodegradation consists of three models. First, with the concentration of bioavailable metal ions in co-contaminated environments increasing, the inhibition of organic biodegradation increases progressively. Second, low metal concentrations promote the biodegradation of high metal concentrations inhibit. Third, low metal concentrations inhibit biodegradation and high metal concentrations inhibit less. The presence of metals can inhibit the degradation of pesticides in soil. The complexity of effects of metal toxicity on organic pollutant biodegradation in contaminated soil and water environments stems from the fact that heavy metals may exist in a variety of chemical physical forms, namely soil adsorbed species, soluble complex species, and ionic solutes. There are three types of pesticide effects on metal bioremediation. First, with the concentration of pesticide in co-contaminated environments increasing, the inhibition of metals bioremediation increases progressively. Second, the process of pesticides with a certain concentration of pollutants promote the removal of metals. And third, the presence of pesticides has no effect on metal removal. However, the presence of pesticides can also be positive. The adverse effects of CD on maize were mitigated by the presence of atrazine, and the CD adsorbed by maize roots was increased. Zinc assimilated by filamentous fungus Phycilomyces marquendi strain was stimulated by alacor. The presence of pesticides may have positive or negative effects on the bioremediation of heavy metals in soils. For example, the residual of organic pollutant in soil may change the soil hydrodynamic, thus change the residual rate and mobility of metals. The coexisting pollutants change the bioavailability of heavy metals. Pesticides affect the behavior of heavy metals on soil organic matter and the surface of minerals, which leads to the change of activation potential of heavy metals in soil. The coexisting pesticides change the amount of secretions and ultimately change the extent of heavy metals uptake by plants. The formation of heavy metal pesticide complexes can occur outside of organisms, and the bioavailability toxicity of heavy metals are changed. Meanwhile, some organic pollutants may passively penetrate the cell membranes without any carrier, which can therefore the penetration of metal or metal complexes into the cell. Pesticides may alter the structure and functioning of cell walls and membranes, thus affecting the penetration of metals in microbial cells. The efficiency of bioremediation is strongly dependent on the illoquium density, the survival, colonization, competitiveness, microbial growth, and the physical diffusion capacity. The indicator of a successful bioremediation is based on the survival of the species. The number of cells died after inoculation should be within acceptable limits. The interactions between inoculants or plants and autoconcus creatures are key roles in the bioremediation process, such as niches, predation, and the competition for nutrients. After survival, bioremediation is also affected by biological activity and manufactors that can affect biological activity such as species, biomass, ease of harvest, nutrient sources, plant growth depth, quantity and composition of exudates, rhizosphere environment, root density, suitable temperature, moisture and pH range, symbiotic species, and the tolerance and accumulation of a range of metals in the shoots. Also, the vitality of inoculants may be inhibited for the toxic intermediates of pollutants, and the degradative capabilities of the inoculants may be reduced during the bioremediation processes. If too much microbial viability has lost during inoculation, The goal of bioremediation is hard to achieve. Furthermore, the other essential characteristics that are required to be persistent and functionally active in target habitats need to be taken into account in the search for target organisms. In summary, the successful bioremediation of pesticides with metals in soil needs a set of biotic factors and abiotic factors in order to maintain the bioavailability of pollutants and the bioremediation ability of organisms.
Good day everyone, I'm Edmar Barnachea and I was tasked to present it to you the fourth part of the journal, which is the bioremediation mechanisms. Residual or leftover of metals and pesticides are the current environmental problems due to utilization of organic products from various production factories and mainly affects the specified bioremediation processes. So bioremediation is the use of microbes and even plants to handle pollutants like heavy metals and pesticides. This is an effective and excellent procedure in remedying or overcoming co-contaminated soils caused by the different pollutants. Microbial remediation is a microbe-use technique under bioremediation to eradicate or preventing any movement of contaminants within the environment. These microorganisms reduce or other organic pollutants into end products or into metabolic happenings. These are the methods of microorganisms remedy metals. First is the binding. Many microbial pathogens bind host cell antigen receptors. These interactions are promoted either by host protein binding the microorganisms or by surface localized ligand encoded by the pathogen. Second is the immobilization, which is the conversion of an element from an inorganic to organic form by microorganisms under conditions of nutrient limitation. And lastly, the oxidation transformation, which is a process in which an electron is taken away from a molecule and transformed into new one. In microbial remediation, there are 5 subclasses of metal pesticides contamination. These are the bioabsorption, bioaccumulation, biotransformation, biomineralization, and biodegradation, which I will be discussing now their definitions and contents. First is bioabsorption. Bioabsorption is a number of metabolism-independent processes by which pollutants tend to connect themselves to organisms. Any organisms has a close relationship for both inorganic and organic pollutants, meaning that there is an immense bioabsorption ability in various organisms. This technique involves several processes such as complexation, which is the association between 2 or more molecules to form a non-bounded entity with a well-defined stoichiometry. Second is the electrostatic interaction that occurs between charged particles in terms of microbial transport. Repulsion is the dominant electrostatic interaction because surfaces of materials are generally negatively charged. Next is the ion exchange, a process that allows the split up of ions and polar molecules based on their connection to ion exchangers. And the other one is the physical and chemical adsorption, which is a forced adsorption of molecules on the material in a strong chemical bond. Next is diffusion, which is a physical process that refers to the net movement of molecules from a region of higher concentration to one of a lower concentration. And the second one is chelation, is a type of bonding of ions and molecules to metal ions. And lastly, the microprecipitation that is often appears in publications about bioabsorption. Bioabsorption is mainly occurs in the cell wall which is the structure of the cell, because the cell wall of microbes is the first structure which blocks or hinders the entering of these pollutants into the cells. The mechanisms of bioabsorption may be operative synchronously to varying degrees, like in the case of lipophilic property of hydrophobic compounds that allows them to travel along the membranes and be assimilated into the organic origin. This suck up of compounds responsible by the fractional groups such as amine, hydroxyl, and etc. is essential on the bioabsorption of organic pollutants. Surface bonding is the main phenomenon of metal ion bioabsorption caused by the ion exchange mechanism of biomass, and this biomass ion exchange involves opposition of protons and metal ions at binding sites like carboxyl and phosphate groups for metal cations in bacteria cell walls, which are negatively charged and abundantly available. Amine groups participate in the removal of metal ions through causing cations to react with another molecule and to collect an ion in condensed form or on a surface via electrostatic interaction or hydrogen bonding. The bioabsorption of lead 2, nickel 2, and chromium 6 ions by Saccharomyces cerevisiae is based on physical collection and exothermic nature of reactions. The interaction of pollutants such as heavy metals and pesticides can affect bioabsorption process. The same active binding sites or mechanism of metals and pesticides lead to intense collection competition. The competition among various types of contaminants depending on their binding connection to the adsorption areas. Low concentrations of pollutants occupy their unique high energy adsorption sites, while high concentrations the complexation between two pollutants can advance or restrain the adsorption of two chemicals. Second is bioaccumulation, is the process by which pollutants enter to the structure of the cell outside of the nucleus, which is the cytoplasm, via the cell membrane and goes directly to metabolic cycle of the cell. These pollutants can have harmful effects on the biodata through this process. But bioaccumulation is controlled on the united physical, chemical, and biological mechanisms. It happens when the concentration of biosphere is not equal to the surrounding environment. This process is also affected by the coexistence of organic pollutants. Third is biotransformation, which is a process by which metals cannot be decomposed or decayed, but they can be transformed into another form of either a low water-soluble or low toxic state due to their altered physical and chemical properties. During the effectiveness of this technique, it depends on the enzymes or metabolism components of organisms. Microbial remediation, such as bacterial and fungal, can be aided with phytoremediation, in which plants may produce exudates to assist bacteria and fungi, shielding from toxicity and supporting xenobiotic co-metabolic activity. Next is the biomineralization, which is a process of converting ionic metals into solid state minerals in cells and particular tissues under the inhibit or influence of biological organic matter. It is divided into two, namely biologically induced mineralization, which occurs outside the cell or the environment surrounding the cell. The extracellular polymers secreted by the cell to sustain nucleation sites for metal ions, and biologically controlled mineralization involves two ways. First is cations are carried across to the inside of the cell and burst to the organic origin. Second is cations are joined in the cell to outline vesicles, and these vesicles are deported to the outside of the cell and split up in the organic matrix to free cations and form many minerals. Next is biodegradation, which is also a process by which microbes reduce pesticides through the utilization of microorganism enzymes to decay pesticides into simple molecular compounds. Metabolism of pesticides in soil organisms involves three-phase procedures. In phase 1, pesticides are converted into product that is highly water-soluble and less toxic than its parent through oxidation, reduction, or hydrolysis, which is the breaking down of molecules. In phase 2, pesticides are joined together to amino or sugar acid, augmenting water solubility and diminishing toxicity compared with the parent pesticide. And phase 3, metabolism components from the previous phase, which is the phase 2, are converted to secondary conjugates that are non-toxic end products. Enzymes play an important role in each phases, like in the case of hydrolysis, which is an enzyme that catalyzes the hydrolysis of several major biochemical classes of pesticide through carbon halide bonds and etc. These are the effects of coexistence, heavy metals, and metabolic degradation of pesticides. The low heavy metal concentrations can enhance pesticides biodegradation for the formation of enzyme metal substrate complexes in which metals may act as cofactors or enzyme and enlarge the activities of reducing enzymes. The reciprocal action of effect between heavy metals and enzymes included in bioreduction of or general metabolism restrain the biodegradation of pollutants. And metals could tie to other functional groups that can be bind to pesticides, thus also restraining the degradation of pesticides. Now we proceed to phytoremediation. Phytoremediation is a process that uses vegetation and rhizospheric microorganisms to administer with the metals and organic pollutants contaminants. Organisms are selected to concentrate pollutants from the environment and then cause molecular breakdown. This process involves several strategies, namely phytoextraction, volatilization, phytostabilization, phytostimulation, stimulation, and phytodegradation. Let's commence with phytoextraction. Phytoextraction is the absorption of contaminants from soil water to penetrate and pass through the roots and causing to change location and collect materials and plants. Its intention is to collect relevant amounts of contaminant and stock it in plants, which later gathered in and arranged. Extracted contaminants can enter into the plants on two routes. First is the soil-to-plant pathway, which contaminants near the root surface uptake by the roots and deliver into the shoots and leaves via the xylem vessels. Second is the air-to-plant pathway, in which particles consisting of heavy metals are entrusted for safekeeping on plant surfaces, whereas airborne pesticides are either adsorbed or on the leaves or deposited on plant surfaces. Phytoextraction of pesticides governed by their hydrophobicity. These are the effects of the coexistence of heavy metals and pesticides to this process. Both heavy metals and pesticides can affect the contents and quantity of roots exudations, and plant lipids play an essential role in absorbing of hydrophobic organic compounds on the root systems. Next is the phytovolatilization. Phytovolatilization is the uptake of contaminants by plants and transform these from original into unstable forms in plants and bursts into the atmosphere through transpiration, the giving off of moisture through the surface of leaves and some parts of the plants. The emits of vapor of contaminants via steam and trunk and hyphenated compounds directly in from soil indirectly because of plant root activities. There are two types of this process. The first one is direct phytovolatilization, which is the high intuitive and better studied form, is the process that contaminants plant absorbing and changing its location, eventually forming in it unstable from the plants. Second is the indirect phytovolatilization, the multiplication in underground unstable formed pollutant flux resulting from the plant root activities. Next is the phytostabilization. Phytostabilization is a maintaining process or stabilizing process which utilizes vegetation for disparaging or preventing the exchange of pollutants at contaminated areas. Its goal is to decrease or reduce the movement and the rate of pollutants and reducing their causing of liquidation to filter down through some material and their entry into groundwater and food chain. Plants stabilize pollutants by reduction of bioavailability through precipitating within the root zones or adsorption on root surface. And the second one is the altering the chemical form of pollutants by root exudates the soil environment around plant roots such as pH, redox potential, and organic content. The second means of stabilization of the plants is the reduction of movement via establishment of developed roots significantly reduces water percolation, wind and water erosion, and limit contact with pollutants. Radial oxygen loss, or the ROL, is a process that the amount of oxygen supplied to the root parenchyma released into the rhizosphere. The iron plaque, or the IP, is formed by the ROL that can remove or separate metal and metalloid on root surfaces and rhizospheres by adsorption and or co-precipitation. The fourth one is phytostimulation. Phytostimulation is a process that reduces organic pollutants by rhizospheric microorganisms in the plant rhizosphere, which is the active habitat around the root zone of the soil that is spread 1 to 2 mm from plant roots and comprises an increased number of microorganisms, which is 10 to 100 times greater than bulk soil. The plants excite their rhizosphere populations in different ways. First is plants sustain attachment to surface such as a period of advance to microorganisms for their development toward maturity and increase profusely. Second, plants invigorate microbial activity by releasing root exudates and improving the availability of soil moisture, oxygen, and nutrient conditions. And the last one is the plant root exudates change the rate of contaminants in the soil. The coexistence of heavy metals and organic pollutants can affect plant root development, and microbial activity. The secretion and composition of root exudates, the presence of the pollutants themselves, benefits that rhizosphere microbes provide to plants can be divided into stabilize and promote plant growth and facilitate the host plant to overcome the stress of pollutants. Biodegradative bacteria are able to reduce organic pollutants. The PGPR or the plant growth promoting Gizobacteria form various plant growth promoting substances or metabolites such as phytohormone. Some PGPR can provide nitrogen and phosphorus for plants through fixing nitrogen in the air and transforming insoluble phosphorus into soluble form. Second, PGPR excretes various other metabolites that reduce the plant stresses caused by the pathogenic attack and organic pollutants and heavy metals phytotoxicity such as biosurfactants and antibiotic compounds. Heavy metals may decrease the enzyme activity in soil and prolong the half-life of organic pollutants. The low concentration of heavy metals can stimulate the rhizosphere microorganisms and promote the degradation of organic pollutants, while the high concentration of heavy metals reduce microbial activity and hinder the degradation of organic pollutants. Fifth is the phytodegradation, which is the transformation of organic pollutants into the less toxic, less movement, or highly stable forms through the action of plant enzymes that does not depend on microbial community. The phytodegradation of DDT and Elodea canadensis and Puraria tanbergiana may be catalyzed through the reductive dechlorination by a chiral enzyme, cofactor, or other achiral biomolecule. In phase 1, the conversion reactions are catalyzed by induced endogenous enzymes. These enzymes react with common functional groups of pesticide such as iodine, chlorine, and bromine through hydrolysis, oxidation, or reduction reactions. In phase 2, pesticides join to different enzymes through the addition of the sugar moiety or tripeptides to contaminants or new conversion products. While in phase 3, plant metabolism is limited to compartmentation and storage, but this mechanism is limited only to organic pollutants because metals are not biodegradable. Lastly, we are on now in soil fauna and bioremediation. Fauna refers to all of the animal life as a descriptor of all the life in a region and relieves soil pollutions by direct uptake, accumulation, conversion, and decaying, in making the better the soil properties and fertility, and promote plant and microbial growth. Soil animals like earthworms can be used as natural indicators of the environmental contamination because it has the ability to uptake those contaminants in the soil and the movement of pollutants into food web where they can be observing in laboratories through their intake of food and soils composing of pollutants. They also promote land reclamation and amelioration. Earthworms can accumulate many heavy metals and pesticides from the surrounding soil environment, mainly through two ways. The first way is the dissolved fraction in the interstitial water had been absorbed through the body wall, and the second way is the intestine absorbs contaminants through the digestive system of the earthworms. And earthworms can also augment microbial activity and enhance the bioavailability of organic pollutants to increase microbial degradation.
Evaluation of soil remediation is important because it ensures the effectiveness of soil remediation and it removes the ecological risks present in the soil biome. It serves as a guidance for post-treatment and reusage of soil. It ensures that the pollutants are removed and it is no longer a threat to human health and the soil biome. Effectiveness evaluation of soil remediation. Here are a few things to remember. Application of contaminated soil remediation procedures, subsequent monitoring, and evaluation methods are needed to assess the remediation effectiveness. This is an important procedure done after the soil remediation. It ensures the effectiveness of the soil remediation as it serves as the guidance for post-treatment and reuse of soil after remediation. There are three evaluation methods of soil. The first is pollutants, second is soil characteristics, and the third is ecotoxicological tests. The content of pollutants in the evaluation methods is important because it shows the current pollution degree. Second, the effectiveness is determined by comparing the before and after pollutant content of the soil. Third, the evaluation based on the pollutant content is using simple and direct method. Fourth, chemical forms analysis of metals in a bioavailability study can provide a different perspective for evaluation. Last, multiple bioavailability evaluation methods were studied to evaluate the remediation effect. For example, cyclodextrin extraction, isotope dilution method, mild solvent extraction, polyethylene devices, semi-permeable membrane devices, polyoxymethylene devices, supercritical fluid extraction, solid phase microextraction, and last, Tenax extraction. Here are a few things to consider about soil characteristics. After the contaminated soil was repaired, some soil characteristics will be amended such as pH, cation exchange capacity, soil structure, and soil enzyme activities. For pH, immobilization of metals generally results in a small increase in the pH value. Cation exchange capacity or CEC is broadly used in soil characterization to assess soil nutrients, retention capacity, fertility, and protection against cationic contaminants of groundwater. For soil structure, remediation has an important effect on soil structure that plays an important role in soil function. The change of soil structure must be considered when evaluating the effects of soil remediation and reuse. In addition, nutrients and water retention, organic matter content, mechanical strength, and electrical conductivity of soil are also influenced. The third evaluation method is ecological risk and ecotoxicological tests. The evaluation of remediation effectiveness concerns the change of ecological risks and the new risks brought by these treatments. Natural organisms and soil ecosystems are now used to develop ecotoxicological tests, and it has been a hotspot in the field of ecological risk assessment. The four areas of focus are phytotoxicity tests, animal toxicity tests, microbial toxicity tests, and risk to human health. Validity of the evaluation methods. Valid evaluation methods can exactly reflect the actual remediation effect of contaminated soil. Here are the principles in selecting evaluation indicators: stability, consider stability and observe whether the corresponding evaluation factors can maintain stability in a certain period of time, so that the errors caused by different measuring time can be reduced. Second is representability. It is convenient to choose the evaluation factors that are easy to measure and has a good correlation with pollution factors. Last is real-time monitoring. It is required for ensuring data validity. Another thing to consider in the validity of the evaluation methods is the hyperspectral remote sensing. It can obtain the physical and chemical information of plants in a real-time, high-efficiency, and non-destructive method, which provide technical support for effective evaluation of phytoremediation effects.
Good day everyone, I am Kris Under A1 from Mariano Marcos State University College of Teacher Education, and I will be discussing about the conclusions and future perspectives of the journal. Conclusions and future perspectives. There are co-contaminated soils with heavy metals and pesticides in the environment. These pollutants pose risk to natural ecosystem and even adversely affect human health. Bioremediation has been proved to be effective in remediation the co-contaminated soils. The remediation of co-contaminated soils is complex. Bioremediation is environmental friendly and has great potential as a remediation method for co-contaminated soil. In order to promote bioremediation co-contaminated soils, the following aspects should be paid attention to in future investigations. 1. Many reported studies were investigated under artificially controlled conditions in the laboratory. The design of experimental parameters should try to simulate the natural conditions, including climatic, weather, and pollutant conditions. Fast-growing plants are possible direction to consider. 2. When targets for remediation involve organic pollutants, remediation strategies should be developed for the organic pollutants, parents, and their metabolites, not just for the organic pollutants parent. We should pay attention on the situation that some metabolites of some organic pollutants have a long half-life or even more toxic than the parent pollutants. Number 3, the plants and microorganisms that had been used for the bioremediation of contaminated soil need subsequent treatment to avoid secondary pollution due to the death of organisms or the changes in the environment. The post-harvest management of plant biomass may be developed in these directions, including bioenergy production, paper making, wood processing, and so on. Biomass that cannot be used should be disposed as hazardous waste. Number 4, the mechanisms of the interaction of different pollutants and the bioremediation and or phytoremediation processes need further research. Meanwhile, research on the elucidation of mechanisms of the plant microbe, plant-to-plant aging, further work should be required to verify the bioremediation efficiency in field conditions rather than in the pot experiments. The field applications should be performed at different locations, and it is necessary to screen potential new hyperaccumulator species naturally or artificially with practical applications. For commercial applications, ornamental plants, landscape plants, bioenergy plants, and micro-microbe interactions under pollutant stress is required. And lastly, the soil pollution assessment methods before remediation and the effectiveness evaluation after remediation should be more high precision, integration, intelligence, low energy consumption, and speediness.